Well, this series of videos is going to continue in talking about the life cycle of a star. And we've been making certain hypotheses about what happens to a star as they go off the main sequence to red giant phase and planetary nebula and so forth. Well, what evidence do we have that this might be right? So that's something we'll investigate here. In this particular video, we'll focus on star clusters that do provide evidence that the models of the changes that happen to stars are correct. In a different video, I'll talk about remnants of low-mass stars and the Type 1a supernova. So some questions that we would have, as I've hinted at here, astronomers want to check to see if their ideas might be correct as they predict different stages of a star's life. And then what happens to the star when all the nuclear fuel is gone? For the sun, hydrogen goes to helium, helium forms carbon, but the mass of the sun is not high enough to create temperatures at the core where carbon will fuse together. So what happens in that situation when the sun runs out of energy in the core? So we're talking about the remnants today, is where we're headed. We've discussed these other stages of the life of a star in other videos. All right, verifying stellar models. And there's a huge problem if, say, the sun has a life of 10 billion years. We have no hope of watching a star be born and die. It's not like a fruit fly in a biology lab where we can watch the development take place. So our solution here is to observe all around our galaxy and in other galaxies and observe stars at various points in their life, and especially the star clusters give some help in providing us data that the stellar models are correct. So astronomers verify their stellar models by observing star clusters, especially observing stars at various points in their life cycle. A star cluster is a large collection of stars, so hundreds, thousands, millions of stars that formed in one location in the galaxy or one location in the universe for these really big systems. We'll focus more on the clusters that formed in our galaxy. That these clusters are going to be in a localized region. We're very confident that they came from one giant molecular cloud, and that's important that they formed in one spot. So let's keep on going with our slides here. Well, let's take a look at some photographs of star clusters, and there are various catalogs. So NGC, the New Galactic catalog, in this entry there, and we'll see other letters for catalog names of clusters of stars. But here we see gas that's not in a star, and then most of the stars in this frame are that one particular star cluster. So one example, we want to look in these star clusters again so we can verify our computer models. When we look at a cluster of stars, it's really kind of, in a sense, a controlled experiment in that some things are the same for these stars. And what might be the same, very likely is the same, that most of the stars in the cluster would form at the same time. There is a little bit of an effect at the larger mass stars. Gravity is able to pull the star together in a shorter amount of time than the low mass stars, but roughly the stars formed at the same time. These stars are all forming out of the gas cloud. We expect in that gas cloud that the composition, hydrogen, helium, heavier elements, is about the same at every point in the cloud. So we've got the same mixture in the elements of the star. And we're about the same distance from the Earth. So as we measure the apparent magnitude, that's very easy to do at a telescope, we can measure this energy output of the stars in a relative sense. And we do not have to spend as much time correcting for distance to the stars. They're all about the same distance from the Earth. So the ones that are brighter because they're really brighter. They're giving off more energy. The other stars in the star cluster that are dimmer, those stars are dim because they're not giving off as much energy. So distance does not play a major role in affecting the brightness of the stars in the cluster as used at the telescope. Our variable here will be the mass of the star. The stars will have different masses that we inspect. There are some other star clusters here. The star cluster M7, the Messier catalog, item number 7 in that catalog. The background here are stars in the Milky Way, but the more distinct blue lights you see here, those are stars in the star cluster. Another cluster here, the Pleiades, very famous star cluster, M45, in the constellation of Taurus, easily visible with the naked eye. In fact, called the Seven Sisters. Depending on the quality of your vision, you can see the 7 bright stars, but there are hundreds of other stars in this cluster as well. And M11, so a lot more stars being located in here. It's not as magnified view of the star cluster. And M4, globular star clusters now that we're taking a look at. And we're getting into the realm here where hundreds of thousands of stars are in the cluster. And as I say, this what we're studying here deals more with the open star clusters, the star clusters in our galaxy. These globular star clusters orbit the Milky Way galaxy. They'll come up as time goes on. So the computer models can be used to collapse the gas cloud, bring us down to the zero-age main sequence, this black line here. And then the model putting in a certain mass, it takes a certain amount of time for the star to get off of the main sequence. There's not time information on these lines. This purple star here is going through much more of its life cycle than the red star down here. So the high mass stars go through their fuel very fast. Low mass stars live longer, and we don't have time information on the plot here, but it's just sort of illustrating how the surface conditions of the stars change. Again, very large stars up in this corner of the HR diagram, and very hot stars off to the left, cool stars off to the right. So the computer models make these predictions, and in the computer models there's time associated with the position of the star on the HR diagram. And the particular very interesting point is the time when the star surface properties no longer have it on the main sequence. This is called the turnoff point for a cluster, and it actually is a way of now determining the age for a cluster of stars. But the high mass stars, those have used up their fuel, their hydrogen fuel in the core, and they've changed into the red giant stars. We have stars that are still consuming hydrogen in their core. Those are the main sequence stars here. And when this star converts a lot of the core hydrogen to helium, then changes happen more rapidly. The star swells up to the red giant stage. And we'll talk about the white dwarf stage cooling off after the nuclear energy is all used up. Observing many open star clusters, and overlaying their main sequence, each star cluster's main sequence, we can make this sort of plot. Now, where do you think on this chart the youngest star cluster is located, and where is the oldest star cluster? The youngest star cluster is NGC 2362. It still has very massive stars on the main sequence. H and Chi Persei is a double cluster in the constellation of Perseus. Fairly young, but a little bit older than NGC 2362. Some of the high mass stars have moved off of the main sequence. And all the way down, here's the Pleiades. It's also a very young star cluster. Coming down here, M3, starting to see older star cluster and more stars in it, so there's data to plot out here. But the oldest one on this chart would be M67. M67. The masses up here, that this M67, it started with the main sequence all the way to the top here, but it's older, and consequently the stars of more mass in this cluster have changed their surface properties of radius and temperature. Luminosity's changed, temperature has changed on the surface, and say this star here used to be over here. This is the oldest star cluster. It has the lowest turnoff point, where the stars are leaving the main sequence is called the turnoff point. It's related to the age. Young star clusters up here have a turnoff point in the O and B type stars. Old cluster like this, we're getting down into the F stars. This particular one, the Sun is a G2 star. So in the F stars spectral class, we're seeing the stars turn off of the main sequence. Here's a globular cluster, and again, very old, and we have here stars still on the main sequence in this globular cluster, M3, but many of the stars have moved off of the main sequence into the supergiants, and coming back here on the horizontal branch, and even starting to pick up some of the white dwarfs that are being formed in this star cluster. So star clusters are used to verify our thinking that the high mass stars leave the main sequence first, the low mass stars remain on the main sequence, and then these star clusters definitely show how these stars are tracking up to the red giant and supergiant realm. And then coming back in here, there's some unstable stars that we'll talk about later in this course. So you ought to write down some questions about star clusters. Star clusters, useful because the stars formed about at the same time, and the stars have about the same composition, chemical composition. The variable is mass, and astronomers can confirm that the massive stars leave the main sequence first. The massive stars have the shortest lifetime. So ask some questions in class.